Okay, let's look at this problem 15 that you voted off the island. This problem 15 involves a ball that is being dropped from rest, and it drops 2 meters. And in the first part of the problem, we're asked, how fast and in what direction is this ball traveling right before it hits the floor? Now folks, this is a one-dimensional kinematics problem, motion problem, but it's also a free fall problem. As soon as you let go of the ball, nothing's touching the ball, and the only force on the ball is the gravitational force. Those are cases where the acceleration is 9.8, let's call it 10, meters per second down. I solved this problem by setting up my list of the 5 variables. Notice that because things are going up and down in this problem, I'm using y instead of x. It's no big deal. I usually use x when things go left and right, and y when they go up and down. Now, every morning when you wake up, you have a God-given right to choose your own coordinate system. You could choose up to be positive, you could choose up to be negative. It's your right. You do not, however, have a right to change your coordinate system in the middle of a problem. Once you choose your coordinate system, you stick with it through the whole problem. I'm going to choose up to be positive and down to be negative. In that coordinate system, my acceleration in free fall is negative 9.8, I'm going to call it negative 10 meters per second every second. Now, the minus sign simply means down. Down. Now, the initial velocity in this problem is 0. I need 3 pieces of information to proceed. The other piece of information is my delta y. Tell your neighbor really quick what delta y would be. Okay, if your neighbor said 2 meters, you've got to slap them for their own good. Okay? The displacement vector is a vector that goes from the very first starting place to the very last ending place as the crow flies. That's a vector pointing down. Its length is 2 meters, but it's down. Okay? In this coordinate system, that means a minus 2. Now, that leaves 2 blank spaces, v final and delta t. I'm looking for v final. That makes delta t the who cares. If I don't care about time, I use the kinematic equation that doesn't have time in it. Now folks, you may have thought that I was just being picky about the minus 2 meters. Not so. If you had put plus 2 meters instead of minus 2 meters, you would be taking the square root of a negative number. If you do that, your calculator will explode. There will be shrapnel all over the room. You don't want to do that. Okay? That minus sign is critical. Now, when I take the square root of this positive number, there are two solutions. Either positive 6.3 meters per second or negative 6.3 meters per second. I chose the negative because the ball is still traveling downward right before it hits the floor. That minus sign, again, is important. In part B of this problem, we let the ball bounce and it rises up 1.5 meters. Now, it was going 6.3 meters right before it hit the ground. Is it reasonable to assume that it left the ground also going 6.3? Why not?
Because it doesn't go back up to 2 meters.
Yeah, if it was going 6.3 meters per second, it would go up 2 meters. It didn't. So it's got to be something slower than 6.3. Well, we can find out just by doing the same process over again. The first thing we put in this list is my acceleration. In this coordinate system, that's still negative 10. 9.8, call it 10. In this case, it's the final velocity that's 0, and the delta y in this case is positive because the ball is traveling upward. again, that sign is critical. I'm looking for V initial. I don't care about time, so I use the same equation. But now it's V initial squared that I'm looking for, so I have to bring this stuff here to the other side of the equation. If I didn't have one of these negative and one positive, again, I'd be taking the square root of a negative number, and that would be a problem. Now here, the answers are a plus 5.5 meters per second or a minus 5.5 meters per second. Since it's traveling up, I chose the positive. Now part C, I suspect, is what got this thing booted off the island. Part C asks for the acceleration during the bounce. And that's going to be V final minus V initial over the time that it takes for the bounce. And by final and initial, I mean at the beginning of the bounce, the end of the bounce. And we're told that that bounce lasted for 0.02 seconds. Now, what's my final velocity? Well, by final, what I mean is this initial. At the end of the bounce, I'm at the beginning of the rise. And so this final is going to be plus 5.5 meters per second. My initial is at the beginning of the bounce. Well, that's going to be this final over here. The beginning of the bounce is the end of the fall. And so that's going to be negative. And here's where it's important to keep track of signs. I'm subtracting V final, and V final is negative 6.3. The minus minus gives me a plus. That's going to give me 11.8 over 0.02 seconds. And that's going to give me a positive 590 meters per second every second. That's a huge acceleration. Okay? That's, well, 59 times the gravitational acceleration, 59g. If that was you, you would be mush. Mush. Okay? Check that your neighbor followed that. Now, folks, I could also have solved this part C graphically if I used the operational definition that acceleration is just a change in velocity vector divided by the time. My initial velocity would be down 6.3 meters per second. Notice I don't put a minus sign there because I've got an arrow down and I'm just labeling that vector with its magnitude. That would be V initial. My final would be 5.5 meters per second up. Now the change vector, if I'm looking for a change, I put them tail to tail. And my change vector is what I have to add to my initial to get my final. That's my change. And that change has to be enough to, there's the plus sign right there. That change has to bring the initial up to 0 and out the other way. And so that is going to give me an acceleration of 11.8 meters per second up over 0.02 seconds. That's going to give me the same answer. Okay. Now, before I go any further, I just want to address something that I noticed as I was picking up your homework. Some of you, when working that problem where you throw the book up into the air, was it 15 meters per second? And it lands a distance 12 meters below, and you want to know how fast the book is going. That's the international symbol of motion. What's that final velocity? Some of you, I'm afraid, are making this way harder than it needs to be. Some of you are worried about how high it goes. And you calculate how high it goes, and then you drop it from rest from up there. You make this a much harder problem than you need to. It turns out all you need to do is go delta y, a, v initial, v final, delta t. If my coordinate system is up positive and down negative, this is going to be a negative 9.8, call it 10 meters per second squared. My initial velocity is going to be a positive because it's up 15 meters per second. My delta y is from the first starting point to the last ending place as the crow flies. That's my delta y. And that's going to be a negative 12 meters. I don't have to worry about this part of the motion. That's taken care of in the equations. Okay? You just have to know how different the final position is from the initial position. Okay? If you did it a different way, you'll still get the right answer, but it'll take you 3 times as long. Questions on that? Okay, I have a check question for you. It turns out you were listening to the radio and they had a contest. You called in and you had the right answer. You're the winner. The prize is a ride in a hot air balloon over Montana. Now, because it's Montana, they let you bring your rifle. And because it's Montana, they let you fire it straight down. There's no one down there. Okay? So there's your gun. I can't draw very well. So you fire the gun straight down, and the bullet leaves the barrel with a velocity of 350 meters per second. My check question is, what is the acceleration of the bullet at a time 0.01 seconds after it leaves the barrel? Okay, talk to your neighbor. What's the acceleration of the bullet 1/100th of a second after it leaves the barrel? Okay. Folks, some of you are doing calculations, and that means I tricked you. Once that bullet leaves the barrel, it has an acceleration of 9.8, let's call it 10, meters per second down. Okay? If we neglect air resistance. Now it turns out that with a bullet, to you hunters, neglecting air resistance is a silly thing to do. With a bullet, air resistance is one of the major factors in whether you're going to take home an elk or not. Okay? But in this class, we're never going to worry about that air resistance. We're always going to deal with cannonballs that are very massive. Or we're going to deal with things large enough that air resistance won't be an issue. In any case, you can always ignore the air resistance in the homework problems, on the exam problems. Okay? Now, what that means is that any time something is in free fall, it has acceleration 9.8 meters per second down. That means if you kick a football, as soon as it leaves your toe, it is in free fall. If you throw a baseball, as soon as it leaves your fingers, it is in free fall. Whether you throw it up, whether you throw it down, whether you throw it sideways, as soon as it leaves your fingers, it is in free fall. The acceleration is 9.8, call it 10 meters per second down. Here's a problem that I think really gets at whether you understand this idea of gravitational acceleration. You and a friend stand on the edge of a 40-meter cliff. You throw a red ball straight up at 30 meters per second. You've got a good arm. At the same time, your friend throws a blue ball straight down the cliff at the same speed. Two questions. Which of those balls, the red one or the blue one, is going to be going fastest right before it hits the ground? Second of all, the red one is obviously going to hit the bottom of the cliff after the blue one. How many seconds after? With your neighbor. See if you can do that in your head. This is not something you would calculate. You would do it in your head. Okay, since we only have 2 minutes, I just noticed the time. Since we only have 2 minutes, let's do it together. You throw the ball straight up at 30 meters per second. 1 second later, how fast is it going? People shout it out. 20. That's what an acceleration of 9.8, call it 10 down means. Every second that goes by, you take your velocity and you add 10 meters per second down. So it would be 20. A second after that, you take the 20 up and you add 10 down, you get 10 up. A second later, you take the 10 up, you add 10 down, you get 0. A second after that, you take 0 and add 10 down, you got 10. The second after that, you're going 20. The second after that, you're going 30. And that's the same speed that your friend threw the other ball, and that means that both of those balls will land at the same speed, but not the same time. The red ball is going to be landing 6 seconds later. That's all there is. Folks, we're out of time. We'll finish this on Friday.